everyone, my name is Syaheera with Ahmad Nazran. I am representing University Technical Malaysia Melaka. Thank you for this opportunity. So my project is titled Real-Time Zero-Shot Object Grounding on the Edge, and is about deploying advanced language guided perception onto the affordable NVIDIA Jetson Nano. Okay, today I'm going to show you how we achieve something that was previously considered impossible on low-cost hardware, making an AI that can understand and find anything you ask for. To understand how we achieve this, let's start with the fundamental innovation. What exactly is zero-shot grounding? So, real-time zero-shot object grounding enables a small, affordable computer like the Jetson Nano to instantly find and precisely point out any object described in a text command. This high level of flexibility is achieved by using a speed-optimized system that can run a large AI model quickly enough, which is 5 to 10 times per second, for real-world applications in robotics and smart surveillance. For the aim of my project is to successfully deploy a real-time flexible vision language model for zero-shot object grounding onto a low-power edge device, thereby validating the feasibility of high-level autonomy in resource-constrained environment. To achieve this, we define 3 key objectives. First, to develop a real-time visual tracking system using zero-shot learning. Second, to deploy and run the system efficiently on the NVIDIA Jetson Nano platform. And third, to design a user-friendly interface for real-time interaction. Before presenting our solution, we must clearly define the major technical problem of project was designed to overcome. So the primary challenge is that the powerful vision language model, which is VLMS, needed for zero-shot grounding are simply too large and complex to run on the small, low-power Jetson Nano. So for the second point is, running this massive model directly on the Nano is far too slow. The resulting inference speed is typically often less than 1 frame per second, which critically fails the core objective of achieving real-time performance, which we set at 5 to 10 FPS. So for the third point is, this incompatibility between the high demand AI and the limited hardware requires a specialized complex engineering solution, specifically optimization to make the intelligent VLM compatible with the severe processing constraint of the edge device. A key decision in this project was the hardware platform. I chose the NVIDIA Jetson Nano over a standard Windows PC because my project requires a dedicated edge AI platform, not a general purpose computer. As shown in the table, the Nano was the only viable choice to meet all my project constraints. So the first one is purpose and speed. The Nano is AI focused, featuring a special GPU with CUDA cores, specifically designed for speeding up my AI tasks. This allows the complex VLM to run quickly, unlike a general purpose PC. So for the second one is the size and portability. The Nano is tiny. This small size is absolutely essential for portability and for integrate my final system into a real-world embedded prototype. So the third one is power and autonomy. The Nano is very low power, requiring only 5 volt to 10 volt. This enables battery power and autonomous operation, which a high power PC cannot offer. So the last one is the real-time focus. The Nano is dedicated and optimized with TensorRT. This dedicated focus guarantees the stable real-time speed 5 to 10 FPS needed for my project objective, whereas a PC is easily distracted by other tasks. This slide illustrates the physical system architecture and deployment setup. The diagram defines the clear roles of the 3 main components, which is Jetson Nano, which is the brain. The NVIDIA Jetson Nano is the dedicated AI engine. It is solely responsible for running the entire optimized zero-shot model on its local GPU, ensuring all complex processing occurs right at the edge. For the second one, camera and inputs. The CSI camera connects directly to the Nano to provide the live video feed. The laptop acts only as the remote controller or user interface, sending the text query commands and receiving the process result. For the connectivity, which is Wi-Fi link, is essential because it validates our solution as a wireless autonomous edge AI system. This allows the Nano to operate untethered and remotely in a real-world environment. This slide shows the successful integration of our system with the actual deployment code. Jetson Nano is the system brain running the entire zero-shot AI model locally on its GPU. The laptop acts as the remote controller, sending commands and receiving the final process results. This Wi-Fi link is essential as it validates the solution as a wireless autonomous edge AI system. So, the code snippets confirm I successfully defined parts and load the pre-trained click model. This VLM is the core technology that enables our flexible zero-shot detection, proving that my optimized and intelligent model is fully operational on the edge device. This slide covers the intelligence of the system. Visual Language Model VLM based on the CLIP architecture. The core idea is the shared embedding space. The model uses separate networks for text and image input. It learns to align these inputs so that a photo and its description are mapped to be mathematically close together. This alignment enables the zero-shot capability. So when you enter a new text query, a new command, the model finds the region in the live video that is the closest match to that text. This allows us to locate an object and output a precise bounding box, even for the object's model has never been specifically trained on. This powerful theory is what we then had to optimize to run fast on the Jetson Nano. This slide explains the core engineering solution. This process transforms the high-resource vision language model into a lightweight real-time engine. So, the step 1 is framework export, PyTorch to ONNX. The first step was to convert the trained model from its source framework PyTorch into the Open Neural Network Exchange or ONNX format. This creates a standardized portable graph structure that is independent of the source framework. For the step 2, aggressive optimization, TensorRT engine generation. This is the most critical step. We feed the ONNX file into the NVIDIA TensorRT compiler. TensorRT aggressively optimizes the model specifically for the Jetson Nano GPU by fusing layers and optimizing memory usage, giving us a massive speed boost. For the step 3, precision reduction. Finally, TensorRT reduces the numerical precision of the weight from FP32 to FP16 or half precision. This technically drastically cuts the memory footprint and effectively doubles the inference speed with almost no loss in our critical zero-shot accuracy. demonstrate the core intelligence of my project zero shot model. After all the optimization, does the AI actually work? Yes, it does. With 3 examples of image text similarity inference. The model takes an image like the car on the road and compares it against multiple text options like a photo of a cat, a photo of a dog, and a photo of a car. The results show that the model correctly assigns the highest percentage to the matching phrase for the car. It correctly chooses a photo of a car with a nearly 100% match. So, for the conclusion, this project successfully bridged the gap between highly complex vision language models, VLMs, and resource-constrained hardware. I just deployed a system capable of zero-shot object grounding, meaning it can find and locate any object based on natural language input. This was achieved by developing a dedicated TensorRT optimization pipeline that accelerated the VLM, allowing the low-power NVIDIA Jetson to sustain a real-time inference speed. In conclusion, the project validates the feasibility of deploying flexible language-guided AI autonomy on affordable edge-based platform for real-world applications.